So what you should do at this point is grab your notebook, wherever it is you normally take notes. This is like the bridge between like, all right, we just did forces and we're moving into motion. What do the forces make things do? Some of these are going to be like overarching ideas that last you this and the next 2 units. So big idea actually for the future. Big idea for next unit is going to be like, what happens if the forces are unbalanced? Right? For today, we could assume that all the forces were balanced, and that means certain things about the motion. Right? So on one side, we have objects that are not in equilibrium. These are objects that have some sort of net force on them, kind of like we were practicing on the first few pages of the homework, where like the net force might be down and to the right. You might push an object forward. Let's say it's the car problem. You might push the object forward with your friend, and friction acts backward. Because there is a net force, that's in this case 550 newtons to the right, force causes mass to accelerate. Is that when you have that net force, it causes mass to accelerate. This is actually a rewording of Newton's second law. A net force causes mass to accelerate. Picture to have in the back of your head here. This is an object that starts at rest. So this is your car and you're pushing it forward. And accelerate means that it travels faster and faster and faster, grabbing more and more distance every second that it travels. Right? If this were like your car and it broke down, right? So your friends are pushing it. If it's dripping oil at equal spaced increments of time, those oil dots would get physically farther and farther apart. So things that are non-equilibrium accelerate, but that means a funny thing. Right? Accelerate means that you are changing velocity. The tricky thing about equilibrium then, and we'll put this as like a kind of box in between these categories. That means if you have balanced forces, if F net equals 0, that means you are in equilibrium. That means you're traveling at constant velocity. But unfortunately, that could mean one of two scenarios. It could be a constant velocity of 0 or a constant velocity of some number, 4, some number like that. So it turns out there's 2 types of equilibrium, and you actually solved both types of problems like that in your homework. So most of your homework problems were about static equilibrium. That's where your net force is 0, the forces are balanced, and you have a constant velocity of 0. Static equilibrium is the state where your object is stationary. All of those ones around our room, our object is stationary. So I know that the net force is 0, and it's going at a constant velocity of 0. Static equilibrium, object is stationary. That would be things like all the setups around the room. All right, so maybe I'm going to draw a picture of like the Barbie and the meter stick one. All right. Can someone give me another object that would be in static equilibrium?
The pumpkin.
The pumpkin. Right? The pumpkin is a stationary object. How about, mechanical engineers. You always want bridges to be in static equilibrium. So maybe I draw a bridge. Maybe I'm not great at drawing, so bridge. We always want bridges to be in static equilibrium. Right? We want our sculptures to be in static equilibrium. We want buildings to be in static equilibrium. For static equilibrium, the object is stationary, net force is zero, and forces are balanced. The other problem that you've done like this is the very last problem of the homework. This is called dynamic equilibrium. And dynamic equilibrium is where your net force is zero, the forces are balanced, and so you're going at constant velocity. Dynamic equilibrium is you have a constant velocity that is not zero. You're moving at the same speed and keeping the same direction. So when I have dynamic equilibrium, sometimes people get confused. They'll be like, the object's moving, so it must have some sort of net force. No. Object is moving at constant velocity, so the force that's pulling forward has to be equal to the force that's pulling backward. If there is more force to the right, it would be accelerating to the right. Constant velocity means that the forces are balanced. So if you are coasting on the highway, coasting means to go at constant speed. So a coasting car going at constant speed, that's dynamic equilibrium. If you have a runner that's running at constant speed, all right, maybe you're like really good at keeping pace. I am not. My runner that's running at constant speed, their applied force forward is equal to the drag acting backward on that. That's why some runners will, like, when they want to train harder, put on parachutes and then sprint. If you watch like the people training for the NFL, they'll like put parachutes on themselves and then sprint as fast as they can. Because if you're going at constant velocity, the bigger the drag force, the more they have to work to go forward. Probably the most important dynamic equilibrium one you can think of would be like a parachute falling at what's called terminal velocity. Right? This is actually what we want when we go skydiving. When you go skydiving, the drag that acts upward cancels the weight of yourself that acts downward. And since those cancel, you can move at constant velocity. You'd have equally spaced dots. So someone taking a picture of you as you fall would see equally spaced photos of you falling towards the earth. So the reason you can solve that lawnmower pushing down problem and still assume it's in equilibrium is look for the key word here, constant velocity. Anytime you see constant velocity, it is in dynamic equilibrium. So that means you know it's automatically net force zero. The forces that pull right equal the forces that pull left.